on Monday at 10 o'clock. And if you have any questions, please post on the EdSTEM forum, or you can just come by one of the office hours. But I'd recommend posting on EdSTEM anyway, just so that others can also hear your questions. Okay? All right. So last class, we talked about Boolean circuits, and we defined this new model of computation, a very rigorous model. We started out by talking about representing things. We went from there all the way to defining a new model of computation. And the model was essentially captured by this directed acyclic graph, right? And then we also talked about why this is a relevant model in our world. One of the reasons is that we can actually implement Boolean circuits in the physical world. You can build devices like transistors and all kinds of other things which can implement the basic operations that we use in our definition. And towards the end, we talked briefly about a new twist here, which was the NAND circuits. So we changed the basic operation from being AND, or not to just a single NAND operation. Okay. So today what we'll do is to study the relation between Boolean circuits and NAND circuits, and we'll also look at one more computational model. And along the way, we'll look at two important ideas. One is equivalence of computational models. This is something that will keep showing up throughout the rest of the course. And probably, if you're sticking to computer science, you'll see this in many forms as you go along. And the other one is the power of Boolean circuits. How powerful are they actually? Okay. Any questions about the last lecture? Okay. So just a quick recap. All right. We talked about the NAND operation. NAND of A comma B was not of AND of A comma B. And we also had NAND circuits. So just as we had some diagrams for AND, OR, and other stuff, NAND has this picture. Okay. It's basically the diagram of an AND with a little dot in front, signifying that you are knotting whatever is coming out of the AND. Okay. And once we have this, just as before, we could build graphs. Starting with a graph, we can build a circuit out of it. Right. So NAND circuits, NMS NAND circuit is a DAG, right? With n vertices labeled inputs, x0 all the way up to xn minus 1, and the other S vertices each has exactly 2 incoming edges. Okay. So one nice feature of NAND circuits is that there is less ambiguity. You don't have to specify what kind of gate it is. It can be, earlier we had to say, okay, this is an AND or a NOT gate. Here, everything is just a NAND gate. So you just have inputs and then you have S NAND gates. That's it, right? And M vertices are also labeled as outputs. Okay. And given such a graph, we can given a NAND circuit, we can define computation, right? So we'll say, you just exactly the same thing as before, compute a topological ordering of the DAG, and then assign values to the gates from layer 0 to the end. Okay? So you compute a topological ordering, meaning you have a labeling, you have a layering of the vertices of the DAG so that the edges are always going from a lower layer to a higher layer, right? So once you have this, you do the exactly same thing as before. For each vertex V in layer I, you assign the value. So for vertex V in layer I, assign value that is the NAND of incoming gates. Okay, that's it. And then the output is a string, which is the value assigned, where the jth bit is the value assigned to the node labeled yj. So, you can define all kinds of things from now on. Maybe tomorrow you have a different kind of gate, not NAND or NOR gate, maybe not OR gate, and you can define NOR circuits, right? So the question now is, are these really different models of computation? Or if they're different, which one is more powerful, which one is actually useful, and so on, right? So we'd like to understand those questions. So how can I answer that? How can I compare NAND circuits to Boolean circuits? Any suggestions? Well, let's maybe ask a simpler question. Okay. Suppose I gave you only a bag full of NAND gates. Okay, your Lego pieces are just NAND gates. Can you compute AND or NOT gates with them? Okay. This should be the simplest question that you need to first understand. If you want to do Boolean circuits as a whole using NAND circuits, or you want to study the relation between the two, let's study the relations between the basic operations first. Okay, so can I compute AND or / NOT with NAND? Let's take them one at a time. Okay, so can I compute the NOT function with only NAND gates? How can I do that? Any guesses? Yeah? Say that again?
You just have the one input come to wire.
Exactly, right? So that's a great suggestion. So the idea is that NOT of a bit, flipping it, is basically the same as NANDing the bit with itself. Okay, so NOT of A is NAND of A comma A. Well, if this is true, we can just check, right? So if A equals 0, then NAND of A comma A which is not and of 0, 0 is going to be 1, right? And if A is 1, NAND of A, A, and of A, A is 1, and not of that is going to be 0, right? So it's exactly mimicking the behavior of the NOT gate. So in other words, the NOT gate is equivalent, like if I had A here, you get nothing. Okay, so if I pass A on the 2 wires, then I get this. And remember, it is fine for us to duplicate variables or to duplicate the outputs, right? You're just putting more wires. That is fine. Okay, any questions about this? All right. So at the very least, we can do NOT. And how about, let's look at the other simple operations that we had. And with NAND. How can I do AND with NAND? Yeah. Exactly, right? So again, this is something that we always do in programming, and we're going to do it again and again throughout this course too, which is reuse the things that we already did. So we just saw how to compute NOT using NAND, right? And I mean, even though it might seem circular, we can write AND of A, B as NOT of NAND of A, B, right? You're just doing double NOT, so you just get the actual AND. And this we know how to do using just NANDs. Okay. So let me also draw a diagram for this. In other words, if I had A, B here, this is equivalent to A, B, and right? So I computed the NAND and doing the NOT by passing the same thing twice through the NAND gate, through a new NAND gate. Okay? So we can simulate a single AND gate with 2 NAND pieces. Right? So simulate AND with 2 NAND gates. And the last piece of the puzzle, let's do OR. Right, so compute OR with AND. How can I do that? Any suggestions? I want to write OR in terms of NAND. Yeah? Yeah, perfect. So you can check this. Okay. So I mean, the intuition here is that OR is basically 1 unless both the bits are 0. Right? So if both the bits are 0, that's when NOT of A and NOT of B, both of them are 1. And when you NOT of that, you just get back the actual OR function. Right, so this is something you can verify by doing calculations. Right? There are 4 possible assignments. You can check that all 4 things lead to the actual answer that you want. For instance, if I put 0, 0, then NOT of A and NOT of B are both 1, and would be 1, NOT of that is 0. Okay? And in terms of NAND, I can write this as okay. Let me draw one last diagram. So this is the OR, and we're saying it's equivalent to this guy. I need to compute the NOT. So I first use that guy. And then I pass it through one more NAND. So we can simulate OR with 3 NAND gates. Okay. How about the white, like the other way? If I gave you only a bag full of AND, OR, or NOT gates, how can I get an AND gate? Not AND. So that's easy, right? So in some sense, we already saw that. So the NAND operation is equivalent to just doing AND and then passing it through a NOT. Okay. So what this is saying is that we can simulate at least the basic operations in using the other set of basic operations we started out with. So in conclusion, both of them are equivalent to each other, right? So that's what all of this discussion is leading towards. Boolean circuits are equivalent to NAND circuits in computational power. Okay, so they might not be equivalent in terms if I restrict you to use the exact same number of gates, right? If I gave you 1,000 AND or NOT gates and then I gave you exactly 1,000 NAND gates, there may be a difference, right? But if I don't limit the number of gates to be used, both of them are equivalent to each other. Okay, and equivalent here, let's spend a couple of minutes trying to make it precise. What would it mean to say the two models are equivalent to each other? What should it mean? It's the most natural thing that you can imagine. Yeah. Yeah, exactly. Right. So equivalent here means the suggestion was that if f is a function that is computable by a Boolean circuit, if and only if f is computable by a NAND circuit. Okay, so recall that we said a function can be computed by Boolean circuit if there is some circuit such that on every input the output of the circuit matches that of the function. And we're saying the two models, Boolean circuits and NAND circuits, are equivalent because they essentially, for any function, if there is a Boolean circuit computing it, then there is a NAND circuit computing it, and vice versa. Okay, so if you have, let's say, a function you're trying to compute is addition, and you came up with a Boolean circuit, there is also an AND circuit for it. Okay? All right. So, I mean, the proof is something that we already saw, but let's just write down the steps. We have to show equivalence. So, in the equivalence, there's an if and only if. So, we have to show the two directions. We have to show that if there is a Boolean circuit computing F, then there is an AND circuit computing it, and then the vice versa. So let's just walk through the steps here because we'll see more complicated versions of this statement later on, and the logic might be confusing then. So we want to show that if F has a Boolean circuit, C, then it has a NAND circuit. Right? So how can I do this? I'm telling you there is a Boolean circuit. Here's a DAG which computes and the corresponding Boolean circuit which computes the function F. Why does there exist a NAND circuit doing the same? Why? Well, we already saw pretty much what we have to do, right? So what you have to do is for every gate in the Boolean circuit, replace it with the corresponding simulation via NAND. Okay, you look at your Boolean circuit, look at each gate and replace it with the corresponding version that only uses NAND gates. If there is a NOT, just put two wires and an AND. If there's an AND, we had this other diagram, just replace that and so forth. Okay. So example, if you had an AND somewhere, you change it to like this. If you had an AND piece, then you put in the NAND circuit for AND. Okay, and so forth. Any questions? And last but not least, let's see if F, we have to also show the other direction. So if F has a NAND circuit, then we get a Boolean circuit by replacing every NAND gate with and NOT. Okay, so we saw how to compute NAND using just AND and NOT. So just do that. You start with a NAND circuit, replace every gate, and you get back a Boolean circuit. All right. Any questions about this? So just as a remark, what we are really saying is that if we start with a size S Boolean circuit, then we get a size 3 times S NAND circuit. Okay, size at most 3 times S, because for NOT we needed only one NAND gate, but for an OR we needed 3 NAND gates, right? So there's some blow up in the size of the network, size of the circuit, but that's fine. We are okay with increasing the size. We're only interested for the time being on whether or not you can compute something even. Okay. And conversely, if we start with a size S NAND circuit, we get a size 2 times S Boolean circuit. Okay. All right. So what did we do so far? We defined two models, both of them are equivalent, and you can now consider all kinds of other circuit models. Maybe tomorrow you'll have a different basic operation. Maybe the different basic operation you have is majority. Okay, so maybe somebody comes and says, okay, your Lego pieces are majority on 3 bits. Can I use this to compute and or not? Okay, you can ask all of these questions and study them. But to make the discussions going forward easier, I want to introduce one other model, which is essentially the same as NAND circuits, but makes some things a little cleaner in the proofs that we'll see. And also ties with the traditional programming structures that you might have seen already. Okay, and this is the language of NAND circuit programs. Okay, so a NAND circuit program, yeah. Doesn't have to be. You can do 3, 4. That's fine. You know, it depends on what are the basic operations to start with. But you don't want it to be something that grows with the size of the input, right? You want it to be basic enough that, you know, maybe it's 3 inputs. Yeah. So with the size, we have all words that Oh, no. Okay, now I understand your question. So the basic operations we are starting with are only on 2 inputs. Okay, so OR is only on 2 inputs, right? So these are like fixed Lego pieces that you're starting with, and then you're building bigger things. So if I had to compute OR on many bits, then I have to only use these basic operations some way to compute the OR on many bits. Okay, so the basic operations should not change based on the input size. Okay, because they kind of somehow we're imagining someone manufactured them and gave them to us. That's it, right? Any other questions? Okay. So the final thing we look at is NAND circuit programs, and here the definition is very similar to everything that we've seen, but syntactically it's a little easier to deal with what we're going to do. So a NAND circuit program is, or NCP, is a string of S lines. Okay, so earlier we were having S gates, and now we have S lines. Okay, hold on. So NCP on n variables, x0, x1, all the way up to xn minus 1 is a string of S lines. Okay, imagine a text file, you have S lines in them, where each line is of the form okay, so each line is exactly of this form. It's an assignment of a variable to NAND of 2 other variables. That's it. Okay, that's the entire string. There are S such lines, right? And where bar comma blah are either input variables or variables from previous lines. Okay. So you're just writing like, okay, I'm creating a new variable temp1, which is NAND of x1 and x5, right? And then temp2 is NAND of temp1 and x10, right? And so on and so forth. That's it. And somewhere we also have to specify the output variables. So some m variables are y0, y1, all the way up to ym minus 1. Okay. So at some point you have m variables which are actually named y0, y1 up to ym minus 1. So for example, you could have temp1 is NAND of x0, x0 maybe. Temp2 is NAND of temp1, x5. And then maybe you have y3 is NAND of temp2 and temp1, whatever. Okay. But this is the entire program or circuit. But this is a computational model. Okay. And this is a description of the model. How do you actually compile it or run it or compute it? So what should I do if I want to compute it? Well, I'll again do the natural thing, which is go step by step. Right? So you start by assigning values to the input variables. And assign value to each line based on previous values. Okay, so you just go line by line. I have the values for x0, x1 through xn minus 1. Temp1, I assign a value, I just compute the NAND. Temp2, temp3, temp4, y0, y1, whatever, right? And the output again is the string, which is 0, 1 through m, with the jth coordinate equal the value assigned to the variable named yj. Okay. Any questions about the model? It's very simplistic. Yeah.
Does this model allow for circular references?
No, because well, actually it could. That's fine. Yeah, but circular just mean that can I reassign a value to a variable?
Or I mean, reassign a variable to a value that's contingent on what the variable currently is.
No, that's not allowed, right? So if you look at the definition, so this bar and blah are either input variables or variables from previous lines. Okay, so they have to have appeared before the current line.
Okay, so you can say temp2 gets something, and then the next line you can say temp2 gets NAND of temp2 and temp1.
That's fine, but you can't say that temp2 is NAND of temp5 and temp7, and then temp5 is NAND of temp2 and temp2. You can't have like something that is looking forward down the program. Okay? Previous is fine because you already have a value to it, and then you reassign. Okay? Yeah? Temp1 is line 1, temp2 is line 2. Yeah.
Like y, like in the y output, temp1 would go into the y.
Not necessarily. So we haven't. I mean, I haven't written the entire code. So I wrote y3 first, but y0 and y1, y2, they could be somewhere down the program. It's not necessary for the y's to appear in the order, that we want them to be. Okay? As long as they appear, it's fine. But if you make things simpler, you can also place this constraint that a variable cannot be on the left and right. Okay, it's not going to change the actual computation. But maybe it's it's a better thing to keep in mind. Any other questions? Okay. And just as before, now we have a new computational model, right? So we can say a function f is computed by a NAND circuit program if there is a NAND circuit program whose behavior matches the function that we want to compute exactly, right? So the question is, how does NAND circuit program compare to the other two models that we saw? What do you think? Remember, here there are no DAGs, nothing. It's just a sequence of lines. There is no graph anywhere, right? How does NAND circuit program compare to NAND circuits or Boolean circuits? Yeah? Can you say it again? It's easier to represent. Maybe. I think that is partly true. Although, even though it seems easier, there is some catch, which we'll get to later. But let's say we're not interested in the size or how many lines for now, but overall computational power, right? If there is a function for which there is a NAND circuit program, would there be one? Would there be a Boolean circuit for it? Yeah. Exactly, right? So the point is that even though it seems like we did something here, we really didn't do much. We end up with the same computational model. NAND circuit program is equivalent to NAND circuits. Okay? Meaning, for any function, if there is a NAND circuit program, then there is a NAND circuit and vice versa. Right? So let's see why. So suppose F has a NAND circuit program. How can I get a NAND circuit from the program? Well, as suggested, for each line, you just create a new NAND gate. So for each line in the program, create a new NAND gate and add two incoming edges. To the previous gates / vertices. Okay, so you go line by line. For each line, I'm creating a new gate, and whatever variables that line refer to, I put wires to the gates corresponding to them. Okay, and it's going to be a DAG because for each line, I'm adding a new gate, right? So that automatically gives me a layering. The edges are only going from this gate to something that already appeared. So something to the past. Okay. Any questions? And the other direction is also if F has a NAND circuit, then how can I get a NAND circuit program? Well, I need to get a layering first, right? An AND circuit program kind of has a layering explicitly built into it line by line. So go layer by layer of the DAG, and for each gate, add a line. Okay. For instance, if gate I had edges, to gate j comma k, then add line temp I equals NAND of temp j comma temp k. All right. So this is how you would convert a NAND circuit program to a NAND circuit, and vice versa. Both are equivalent. We'll adopt whichever is more convenient for us. NAND circuits, they're more sometimes easier to think of when you're drawing diagrams. For small things, they are cleaner. To talk about things more abstractly, NAND circuit programs are nicer, right? So as was pointed out, there somewhat seems like NAND circuit program you can represent more succinctly. There's no graph, no diagrams. It's just a string, a sequence of lines. Okay? Yeah.
So the NAND circuit program, if you allow you to reassign variables, how would you represent that?
Oh, that's a good question. So maybe let me not do that. Where from previous lines and not full. Okay. So let's avoid that. Maybe if there is such a thing, you might have to create a new gate anyway, right? So let's avoid that. Okay. But it might not, technically speaking, it might not be a problem because you're just creating a new gate every time, right? So in some sense, if you think of Python, for example, right? When you assign a variable, again, like if I say a equals a plus 1, it's really creating a new variable and calling it a as well, right? So something like that. Okay. That's a good question. Any other questions? Okay. So just to summarize, so what did we do in the last class and the first half of today? Summary, we defined our first computational models, okay, and that are grounded in reality, right? So Boolean circuits, NAND circuits, and NCPs for short, NAND circuit programs. And we showed that they are equivalent. And we also looked at equivalence of computational models, which is again a very important concept. So this is the second idea. The first idea was that you can actually implement circuits using physical devices. So it's a very realistic model and something that people used right from the beginning. And second one is equivalence of computational models. You can argue that one model is equivalent to the other if I can somehow simulate one using the other and vice versa, right? But this really is still, we haven't answered the question, are these useful for computing? Okay, meaning can we actually do some useful computational tasks using these Boolean circuits or NAND circuits or whatever? I gave you, maybe let's say 1,000 NAND gates. Can you build me something which multiplies maybe let's say 64-bit numbers? Can you add 64-bit numbers using these many NAND gates? Even if I give an infinite supply, can you do it or can you not? Okay. So whether these gates are useful or not will be determined by what kind of functions you can actually compute with these models. Okay, so let's take a 5-minute break, and when we come back, we'll answer that question. And just as a heads up, from now on, things are going to get more complicated as we dig deeper into the models and study their power as well as limitations. Okay, all right, let's take a 5-minute break. So we defined these Boolean circuits, NAND circuit programs, and now we are asking the fundamental question, did we waste our time or did we do something useful with these definitions? Luckily, I actually didn't waste your time, and they are in fact very, very useful. How useful are they? As useful as they can get, meaning any function can be computed by Boolean circuits, equivalently by NAND circuits or by NAND circuit programs. So every function f on n bits to m bits. Remember, when we talked about the circuit model, the number of inputs was fixed. We only had n bits going in, and we had some number of output bits coming out. And the statement is that every such function can be computed by a Boolean circuit. Of size some number, some huge number. The size has to be at least, or at most, sorry, the size is at most n times m times 2 to the n, where n is the number of variables and m is the number of output bits. Okay? So no matter what function you pick, there is always a Boolean circuit for it. Maybe humongous, but it is definitely possible. Does the statement make sense? Any questions about the statement? Okay. It might seem like it might not seem that surprising that this is true, but later on we will see that for various models there are limitations. There will be functions that cannot be computed no matter how much size or time or whatever resource you have you allow. Okay, but at least for Boolean circuits we have this concrete statement. Yeah. Right. So it will come up. We'll prove the statement, and we'll see why you have such a big, like 2 to the n and something like that. Right. Okay. So let's see why this is true. To understand, or kind of let's investigate why this is true. Right. So to investigate why it is true, let's see what we're trying to actually show. So for intuition, I'm only going to study the case where m equals 1. So the number of output bits is exactly 1. And once I know it for 1 bit, then I can also generalize it to many bits by kind of repeating the same thing for the different output bits. Okay. So let me only focus on one output bit. Now, so we have a function which takes n bits and outputs a single bit. We want to say that any such function can be computed by Boolean circuit. Well, let's think of what this function is doing. I can draw a truth table for the function. Right? Now maybe something like, let's say I have 0, 0, 0, the output is 0, 0, 0, 1, it's 1. Okay, maybe I drew the diagram for 3 bits. This is what my function looks like. This is the truth table, and I had to come up with a Boolean circuit for it. So how can I do that? So we're going to do it in a couple of modular steps. First, to come up with a function that we need to come up with a circuit which exactly identifies which are the 1 inputs, right? So there are 2 kinds of inputs here. Those for which the function actually says the output is 0, and those for which the function says the output is 1. Okay, so let's separate them. So let's say S is the set of all those inputs for which the output is 1. Okay, and any suggestions on how I can come up with the Boolean circuit for this function? You might have seen something like this before, but we'll walk through it slowly. So the idea is that maybe if I can identify whether my input is in the set S, then I'm good, right? If I know my input is in the set of all things on which the function evaluates to 1, then I should output 1, right? It's the same thing. I just rephrased it. I didn't do much progress here. But I'm saying to compute the function is equivalent to checking whether or not my given input X is part of the set S or not. Okay? If it is in the set, then I have to say 1. If it is not in the set, then I have to say 0. Okay? So how can I check that? We will do this by breaking it up into 2 pieces. First, for each alpha or each specific string, okay, so imagine the string is all 1s or all 0s, or maybe all 1s with a single 1 at the end. I'm going to define a new function. A very, very simple function. And what is this function? It depends on the specific string you're looking at, and it just checks for equality. It's a function where on any input, the answer is 1 if the input is exactly the string alpha or 0 otherwise. Okay, these are some special functions among all possible functions on n bits. Okay, these are special for a reason for us, but let's see whether we can even compute these using Boolean circuits. Okay, what we're trying to say is that every function has a Boolean circuit, and I'm asking, can you at least come up with a Boolean circuit for these functions, these seemingly simple functions, which are just checking for equality. So for instance, so let's do an example. Let's say alpha is all 1s. Then what is the function E alpha? When is it 1? It's a function that you already know. What is that function? Well, it's just checking if the input has all 1s in it. Which function checks if the input is all 1s? And, right? So in some sense, this guy, I mean, E alpha is just and of x0, x1, all the way up to xn minus 1. Okay? So how can I compute E1 as a Boolean circuit? And this goes back to a question that was raised earlier. which was, we had and, or, not as our basic operations, but there was a limitation that those basic things can only take 2 inputs at a time, right? You're starting out with these basic pieces. You're allowed to put as many of them together as you want, but those are the pieces that you start out with. Can I compute and on n bits using my and, or, not gates? Yes or no? Yes, I see many people nodding. Yeah. Exactly, right? So remember, we said that and, or satisfy associativity, right? And of n bits, I can compute iteratively. I can compute the and of the first 2 bits and then the output of that to the and of the 3rd bit and so on and so forth, right? So I could do that. So E1111 is equivalent to the following circuit. I think I need to draw this diagram once very well so that I can reuse it. Okay, I'm computing the AND of the first 2 bits here, x0, x1, x2, all the way, xn minus 1. And then I can repeat this. Right, I'm just doing a cascading series to okay. Some of the wires go like this, and you end up with a single output, which is the AND of all the n bits. Okay. All right, great. So I can compute E of all ones, which is a simple function, simple enough, but at least I can do this. Now, how about more general alpha? What if I tell you I want to compute E of all zeros? E of, all zeros with a single one right in the middle. What can I do then? Yeah? Exactly, right? So more generally, if I have a string alpha which is 0, 1 to the n, then to compute E alpha, I can use above figure with some NOT gates. Okay, so imagine alpha was all zeros. Checking that your input string is equal to all zeros, I can follow the same template, except that every x0, I should pass it through a NOT gate first, right? I have to check NOT of that. Checking whether something is 0 is equivalent to checking whether the NOT of that is equal to 1. Okay, so let me do that. Okay. So if I want E alpha, then what am I going to do? I'm going to say put a NOT gate. Put a NOT gate if alpha 0 is 0. That's it. So follow the exact same cascading series of ANDs, but on the wires going from the input nodes to the AND gate, put a NOT gate if the corresponding bit in alpha was 0, right? Because if alpha 0 is 0, that means I am asking you to check whether the first bit is 0, right? And the same thing. Put a NOT gate if alpha 1 equals 0 and so on. Okay. On ith wire, put a NOT gate if alpha I equals 0. All right. Any questions about this? So what this is saying is that at the very least, we can compute these simple or special functions that we define, E alpha, which check whether or not input is equal to a specific string using Boolean circuits. So summary. E alphas can be computed by Boolean circuits for any alpha. Give me any alpha that you want. Maybe it has 1, 1, 10, 1, no ones. I can compute the corresponding equality checking function E alpha using Boolean circuit. And how many gates does it have? How many gates might I end up using? Well, the number of gates is actually at most 2 times n, right? I might have, actually maybe it's more like 2 times n minus 1 perhaps, right? So I might have n minus 1 AND gates and maybe some NOT gates. Maybe if everything is 0, then I have to put a NOT gate in addition. So I end up with these many gates. Okay. Any questions? All right. Okay, so why are we studying these E alphas, right? The reason is that we can actually use this E alphas to compute any function in a clean way, right? And again, we're going to reuse the things that we already did to make things simpler. We'll always be trying to use a modular approach as much as we can. Break up a big problem into smaller pieces and solve the pieces separately. Okay. So concretely, next question is, or let me say, how can I use E alphas to compute F? Okay, I'm giving you as a hint that given that you can compute E alphas by Boolean circuits, you should now be able to tell me why any function can be computed by Boolean circuit. Why? Well, let's go back to this set of 1 inputs, right? So for any F, we have this special set of all inputs on which F evaluated to 1. And maybe I can write this set index in some way as alpha 0, alpha 1, up to alpha capital N minus 1. Okay. Maybe this set has these many elements, some n, big N number of elements. How big can this set be? It can be at most 2 to the n, right? It could be all of the possible strings. It could be empty even. Fine. Okay. Right. And how can I now compute f given I'm here? I have to check whether x is in this set or not, and I know how to do E alphas. Yeah? Exactly, right? So remember checking whether f evaluates to 1 on input. I gave you an x now, and I'm asking you to compute f of x is equivalent to checking whether x is a part of this set. And it is a part of this set only if it actually equals one of these special alpha i's. Right? So it should equal one of these things. But we already know how to check if it equals one of these things. Right? And how can I check if it equals at least one of all of these things? I just take the OR. Okay, so this is an identity. Let's maybe go over this again. F of x is 1 if and only if x is part of this set of all things on which f evaluates to 1. This is a fixed set, depends only on f. We know that already. And I can look at all the elements in this set, alpha 0, alpha 1, alpha n minus 1, and I have to check if x equals one of these things, one of these elements from my set. But I know how to check equality now. I have a Boolean circuit for it. Okay, so I can piece all of them together. As long as it equals at least one of them, I'm good. I have to output 1. So I'm going to take an OR of all of these things. Right? Yeah?
Is there also an assumption that X will be a side element as well?
Say it again, sorry.
X will also be a side element. Is that
Yeah, so f is outputting only a single bit. Yeah, yeah. So, I mean, the statement that we originally started out was with m bits, right? But I said I'm going to prove it only for the case m equals 1 for now. Okay? And once we know this, we can actually do it for all possible m without too much difficulty. Okay? Any other questions? Yeah?
So in this form, like you could go like E alpha 0 and 1 alpha. If alpha 0 is the animal, right?
If we have a 0,
If we have a 0, how many we add them all?
it shouldn't matter, right? As long as at least one of them evaluates to 1, we'll get 1 as the output. Otherwise, we'll get 0. Right? So if x is not in any of these things, then f of x should be 0, and that's what we're going to get. Okay? All right. So this is good. But I mean, this is good in the sense, how can I now finish my Boolean circuit for f? Well, I know how to compute OR on multiple things. How can I do that? I can do the cascading OR, right? So let me do that. Okay, so let's use the full power of the software. Okay, so I'm going to draw a giant circuit. So first, these are the input variables, you know, x0, x1, xn minus 1. Well, I'll do it if it allows me to. Some reason it's not letting me paste. Okay. All right, cool. Okay, so imagine I can do this now, right? We can actually reuse the circuits that we developed. Okay. So this is E alpha 0 of x. And this is E alpha 1 of x. E alpha n of x. Right, so I take the circuit for each of the alphas in my set S. E alpha 0, E alpha 1, E alpha 2. I have a Boolean circuit for each one of them. I put them all one below the other. You know, the inputs are going into everything. Okay, the input wires go into all of these copies, and I had to combine them using one giant OR. Okay. All right. So in the end, I get f of x, or output y0. Okay. So that's my Boolean circuit for f. For any f, you have this set of things on which f evaluates to 1. We start with the E alphas for each one of them and stack them together using the OR, and we get our final Boolean circuit. Okay. So this whole thing is the Boolean circuit for f, which is what we wanted to say, that for any f, there is a Boolean circuit. We exactly showed that. Okay. So there's one piece missing, which is counting the number of gates, right? In the statement, there was a bound on the number of gates that we had, but let's check how many gates did we end up using. So number of gates used. So what's the size of this circuit? How many gates did we use in total? Well, each of these red boxes, each of the E alphas uses at most 2 times n gates. Okay, and how many pieces can there be? So number of gates used is at most n times 2n, right? So this is the number of boxes, and each box involves 2n ORs, I mean, maybe 2n gates, at least n minus 1 ANDs and possibly some NOTs. And then we also have some ORs outside. How many ORs do I have? Okay. So I have this cascading sequence of ORs which takes the output from each of the pieces and computes the order. Okay. But how big is this capital N? As you already said, the number of possible strings on which f evaluates to 1 can be at most 2 to the n, right? So it's at most 2 to the n times 2n plus 2 to the n. So n is less than or equal to the n. So there's a total possible that's a possible number of inputs, and the number of inputs on you evaluate to 1 must be at most this much. Okay. So I can write this as O of n times 2 to the n. The exact constant in front is not that important. So we get a Boolean circuit of this size for every function. Okay. And there was a question about where this size 2 to the n came from. Intuitively, it comes up because somehow you're hard coding all of the possible inputs, and the number of inputs is 2 to the n. Okay. Any questions about this? Yeah.
I got the 2 in the first line. Like,
Right. So let's go back here, right? How many gates were there in the E alphas? So we had n-1 AND gates, like this cascading sequence of ANDs, and on each of the input wires, you might or might not have a NOT gate, right? So there are possibly n NOT gates and at most n NOT gates and n-1 AND gates, right? So I'm just using an upper bound. It could be slightly better. It's between n-1 and n plus n-1. I just rounded it off to 2n. Okay? Yeah? Oh yeah, so because there are n possible, there are n red boxes. Okay, so maybe let me write it. We have n of these boxes. Okay, and we're not reusing things. Every time I'm using fresh batch of gates. Right, so there's no sort of reuse, no nothing, no savings there. We're just creating like copies every time. Okay, since each one has at most 2n and you have n copies, the total number is n times 2n. Okay, any other questions? And then we also have these OR gates here, right? Which was n-1, that's this guy. Okay, and in the discussion section, the TS will go over how to generalize this to multiple outputs. But the idea is that you take your multiple outputs. Let's say your function has m different possible outputs. You do the exact same thing for each bit separately. Okay, so let me write that down. I don't want to repeat the same thing. To generalize to m outputs, we can compute each yj using the above method. Okay, to compute a single bit of the output, I take n times 2 to the n. For the second bit, again, I take n times 2 to the n and so forth. So I multiply everything by m, the number of output bits, and I get a Boolean circuit for my function f. Okay? Any questions? All right, so just to summarize, every f from here to here has a Boolean circuit of size okay. So just as a remark, this is not the best possible you can get. You can actually do slightly better. There exists a circuit of size of 2 to the n by n. Okay. We showed a circuit of size n times 2 to the n, but you can actually find circuits of size slightly better, which is 2 to the n by n. Okay. But this is much more complicated and not something that we are going to cover, but the textbook has the details of this more efficient way to construct circuits for all Boolean circuits, for all functions. Okay. All right. So let me just do a couple of things. So now that we know that Boolean circuits as a computational model are very powerful, let's talk a little bit about how efficient they are. Right. So let me say that maybe size nms denote all functions that have a Boolean circuits, all functions on n bits that have a Boolean circuit of size less than or equal to s. Okay. I can also look at limiting the number of gates you're allowed to use and see what functions can I compute. So what we just showed is that if I take s to be m times n times 2 to the n, then that includes all possible functions. Okay. But how about if I allow you only a linear number of gates, quadratic number of gates? Do I always have to come up with this really humongous circuit, like 2 to the n size circuit, even for simple operations like addition and multiplication? If so, that would not be a very useful model, right? I mean, to give you a sense, 2 to the 20 is like huge. You're not never going to be able to write down a circuit or print it out, even if you want to, right? But luckily, the model of circuits is actually a very efficient one, even though it's not something we are talking about in this course. For instance, addition. Right? If I give you 2 n-bit strings and ask you to add them, okay, that's a function. It has a Boolean circuit of size O of n. Okay, so concretely, if I say ask you to compute the function add, which takes 2 n-bit strings and outputs some binary string. And here you should think of the input as, let's say, that is add of x comma y equals x plus y. Meaning this is binary. So x is, I want the output to be the sum of the integers in binary representation. I give you the binary representation of an integer, binary representation of an integer, and the output should be the binary representation of the sum. Okay? And it turns out that if I ask you to compute this using Boolean circuits, you can use our theorem that we just showed and get a circuit of size, m times n times 2 to the n, but that would be really an overkill. And in fact, there is a circuit which only takes a linear number of gates, a much, much smaller number of gates. Okay? And in some sense, in reality, if you think of an algorithm, right? You write some program, each step can be translated more or less into Boolean circuits with some efficiency losses. Okay. So for instance, you can also ask what happens when multiply. Okay. And these are in binary. The output should be binary representation. Well, multiply also has Boolean circuits of size of n squared. Okay, so you can in fact find much more efficient Boolean circuits than using our hammer of a theorem, right? So we just put like we have this seemingly powerful theorem that anything can be computed, but there's a huge bound we are paying in terms of the number of gates. It is n times 2 to the n. And if you are willing to spend some more blood and sweat, you can improve it to 2 to the n by n. The question now is whether or not this is the best possible. Can I get more efficient circuits? For addition, of course I can. For multiplication, yes. If I ask you to compute something for majority, you can do that too. Sorting, all kinds of things you can. But however, every function. Can every function be computed by a Boolean circuit of some small size? Okay. And in the next class, we will answer this. So one of the reasons we define computational models is to look at their limitations. And as we'll see, a limitation of the physical world in some sense and of Boolean circuits is that some functions on n bits cannot be computed by Boolean circuits of size less than, let's say, 2 to the n by 100 times n. Okay. So every function has a Boolean circuit of size roughly 2 to the n by n, maybe something like 10 times 2 to the n by n. But we'll show in the next class that there are some functions which actually require these many gates. You cannot like always get humongous savings on the number of gates, right? These are somehow the hardest functions you can imagine, and talking about computational models that we're doing allows us to talk about those things. Okay, and the way we'll prove it, we'll introduce one of the most important ideas in computer science, which is to view programs as inputs. Okay, and we'll talk about that in the next class. All right. Okay, so I'll see you all on Monday, and remember that the homework is due on Monday.